Hi everyone, so today I'll talk about rational cross-sections. In particular, when do Wreath products have any of those? So let's start with a definition. So we start with a group G and a finite generating set A. Then what we call cross-sections is actually a language, so some set of finite words, L, such that the evaluation map from L to G is bijective. So each word in L can be seen as a product, and you can evaluate it in G. And then rational here correspond to regular here. So I'll try to give a fair idea of what a regular language is using this example. So you should start with an automaton that is a finite graph with some preferred vertex v0, and then a bunch of edge oriented labeled by element in A. And so to each such automaton, you can associate the set of words that you can read along a directed path starting at v0. So that's a typical regular language. So for instance, here if you start at v0, you take this edge and then twice this loop, you will get the word a to the q, which appear here somewhere. And so actually, if you look closely, you can see that this language actually is a regular rational cross-sections for the infinite cyclic group. That's the first example. Then the second ingredient is a Wreath product. So I've written the definition here, but actually you don't need it really. All you need to know is how to see, how to understand a word over this kind of trunking set. So the picture should keep in mind. So you have some space, which is basically a K graph for the space group H. And then on each vertex you have a lamp. Initially, all the lamps are off. And you also have some guy, the lamplighter guy, which is moving on the space, and it initially is at the vertex 0, so the identity. And so when you read your word from left to right, each time you see a letter from H, you tell the guy to move around accordingly. And each time you see the letter A, so the generator for the cyclic group here, you tell the guy to switch the state of the lamp on the side he is on, so either on to off or off to on. So at the end of this process, at the end of the word, you have some finite set of lamps, which is on, and you also have the position of the lamplighter guy at the end of the word. Such an information is what you need to characterize an element. Next slide is basically I want to describe basically morally what we would like to have in order to construct a rational cross-section on a Wreath product. So even though it's not strictly prohibited, we would really like not to change the state of a lamp, of a given lamp, too often. So that's not prohibited, but that would really be a mess, and so we rather not. And so basically what we would like is to enumerate the sites in H and to go through them one by one and change the state of the lamp accordingly. So what we need is some kind of order on H, and the order should be encoded in an automaton. And that's really restrictive, because an automaton cannot keep track of anything, basically. Basically, it can only keep track of in which coset of some finite integer group you are. Finite index group. And so what this implies is that the positive direction should almost always be the same. So which means that the order should basically be less invariant. And also, as it's encoded in an automaton, then the positive direction, so the positive coin here, should be rational in some way. And so indeed, if all of that holds true, then we do have a positive result. We do have a rational construction for the Wreath product. So what we ask precisely is that the lamp group, so G, should be nice enough. It should have a rational construction on its own. And then we should have some finite index subgroup in H, which should be left orderable, and for which there exists some order which is given by some regular language. And so if all that holds true, then we are happy. We have some rational construction. And then the last slide, which is what I'm most happy about in this work, is some negative results. So here we suppose we have rational construction. We suppose we have an automaton. We try to derive some condition and then find some contradiction. So here I start with those two conditions, either of those two conditions. So either G is torsion or G doesn't contain any free subsonic group. And H is torsion free. So if either of those two conditions are true, then we have something really nice when we're building our world in our automaton. So we have some path and we are reading along it. So we can decompose the automaton into strongly connected components. And what happens, and what's the content of this lemma, is that as long as you stay in some strongly connected component, you will move along some chain for some prescribed order on H. So the lambda guy move like that. And so as a corollary, we have that the lambda group on the free group doesn't have any rational construction. So here, even though F2 is left orderable, there isn't any regular total order on F2. Even better, if you give me a finite amount of regular partial orders on H, then I can find some large subset of F2, which is an untied chain with respect to any of those orders. And so if you try to construct the elements where you switch on the lamp on each of those elements in your untied chain, then basically when you're building your words in the automaton, you can only switch on basically one in each strongly connected component. And as we have some only finitely many strongly connected components, we cannot do enough to construct all elements. That's our contract. So that's it. Thanks for listening, and I hope you have a nice rest of the 24 hours.